On November 24, 1944, the first B-29 Superfortresses of the 73rd Bomb Wing appeared over Tokyo. At 12:15 hours, radar operators at Tateyama detected multiple formations approaching from the southeast at altitudes exceeding 30,000 feet. Japanese observers stationed along the coast reported contrails forming thin white arcs against the upper troposphere. No Japanese aircraft in service could reach that operational ceiling with a full combat load. Ground-based anti-aircraft batteries tracked the formation but recorded ineffective fire due to range limitations. Temperature at that altitude was recorded at -45 degrees Celsius. Visibility from the ground was estimated at less than 5 miles due to haze and winter inversion. Observers at the Yokosuka Naval Air Technical Arsenal identified the aircraft as 4-engined, mid-wing monoplanes with pressurized cabins. Each carried a wingspan of approximately 141 feet and a gross weight exceeding 130,000 pounds. The aircraft flew in tight rectangular formations, separated by exact geometric spacing for bombing accuracy. Their engines, Wright-Ubb 3350 duplex cyclones, produced a combined output of over 8,800 horsepower per aircraft. At maximum altitude, their cruising speed averaged 350 miles per hour. Intercept attempts by Mitsubishi J-2M Raiden units from Atsugi and Nakajima Ki 44 squadrons failed due to climb limitations. The B-29s maintained altitude advantage throughout the mission, remaining beyond the effective range of 75 mm and 88 mm guns. At 12:45 hours, bombardiers released payloads of 500-pound high-explosive bombs using the Norden M9 bomb site. Impact points were recorded across industrial sectors of Musashino, Nakajima, and Kawasaki. Reconnaissance aircraft dispatched post-raid confirmed that the pattern density of bombing exceeded pre-war standards by 42%. Observers noted that the B-29s returned on a near-linear course toward the Mariana Islands, refueling in flight not required. Japanese meteorological units calculated that the Superfortress operated within a weather layer inaccessible to existing fighter performance. The first combat report from the Army General Staff described new high-altitude bombers of unprecedented endurance and precision. Radio intercepts confirmed that these aircraft originated from Saipan, captured only 4 months earlier. From Coastal Command to the Imperial General Headquarters, the conclusion was immediate: the air war had entered a new phase. By evening, intelligence summaries from Tokyo's 1st Air Army concluded that defense countermeasures were technically infeasible with existing equipment. The altitude, range, and bomb load combination rendered Japan's defensive perimeter concept obsolete. As night fell over the capital, surviving officers reviewed the day's film records and instrument traces. The altimeter data, verified by recovered fragments, confirmed the operational ceiling, 31,360 feet average across formations. It was the highest sustained bombing altitude yet recorded in the Pacific Theater. Below, the remnants of searchlight beams reached upward but faded long before contact. From that day forward, Japanese observers classified the B-29 as a strategic invader from unreachable airspace. The sky, once a defensive shield, had become a domain of observation only. And those who witnessed the first Superfortresses crossing overhead understood that the balance of altitude and of war had shifted permanently. By mid-1944, the United States Army Air Forces had established the 20th Air Force under direct command of General Henry H. Arnold. Its purpose was singular: to conduct sustained strategic bombing against the Japanese home islands. The operational foundation rested upon the Boeing B-29 Superfortress, developed through an industrial program that consumed over $3 billion. It was the most expensive weapons project of the war, surpassing even the Manhattan Engineered District in scope during its early years. Production lines in Wichita, Marietta, and Renton operated continuously under supervision of the Army Materiel Command. By the summer of 1944, monthly output exceeded 100 completed aircraft. Each unit required over 165,000 separate parts and 60,000 man-hours of assembly. The B-29's pressurized fuselage allowed crew members to operate above 30,000 feet without supplemental oxygen fatigue. Its central fire control system was operated by analog computers linking 5 remote-controlled gun turrets. This system permitted a single gunner to engage multiple targets using gyroscopic aiming correction. The bomber's range exceeded 3,200 miles, enabling round-trip missions from the Mariana Islands to the Japanese mainland. Logistical preparation for these missions began with the seizure of Saipan, Tinian, and Guam during the Central Pacific Offensive. Engineering battalions constructed runways over 8,000 feet long, surfaced with crushed coral and asphalt, to accommodate the superfortress. Each airfield complex required more than 1.5 million cubic yards of earthmoving and 10 million gallons of aviation fuel storage. By October 1944, over 400 B-29s had been deployed to the Marianas under XXI Bomber Command, commanded by Brigadier General Hayward S. Hansel. Japanese intelligence analysts in Formosa and Kyushu initially underestimated the aircraft's effective range, assuming operations from China. They were unprepared for direct sorties launched from the newly established Pacific bases. The first raids on Tokyo marked the operational debut of a completely new form of warfare, high-altitude precision bombing over intercontinental distance. No existing Japanese interceptor had a climb rate or engine supercharger capable of matching such performance. The Nakajima Ki-84 Hay-8, Japan's newest fighter, could barely reach 34,000 feet under ideal conditions, and only with minimal armament. Operational readiness reports from the Imperial Army Air Service confirmed mechanical failures above 28,000 feet were common. Ground Command noted that the B-29s maintained formation stability even in the jet stream's turbulent layers. This stability was a product of power-assisted controls and aerodynamic refinement previously unseen in combat aircraft. Observers from the Army Aviation Technical Research Institute described the bomber as a moving fortress immune to altitude interception. By the close of 1944, Tokyo's defense strategy shifted from interception to early warning and passive protection. Civilians were instructed to shelter in reinforced basements, though few existed in industrial zones. The Imperial General Headquarters began investigating radar-directed night interception as a last resort. But even before the first tests concluded, it was clear that Japan had entered a defensive posture against an opponent that operated from the stratosphere. The arrival of the B-29 redefined not only the range of combat but also the vertical dimension of war. From that point onward, Japan's observers, engineers, and pilots faced a reality dictated by altitude, distance, and industrial arithmetic, domains where the empire no longer held parity. Japanese military engineers began systematic analysis of the B-29's performance following the first raids on Tokyo and Nagoya. Recovered wreckage from downed aircraft provided technical samples for study by the Army Aeronautical Department in Tachikawa. Examination confirmed extensive use of lightweight aluminum alloys and heat-treated structural members unfamiliar to Japanese production. The skin panels exhibited flush riveting, a technique reducing drag by approximately 6% at high altitude. Internal inspection revealed pressurization bulkheads reinforced with magnesium fittings and seal joints. Engine analysis identified the Wright R3350 duplex Cyclone with twin turbo-superchargers enabling sustained operation beyond 30,000 feet. This technology compensated for oxygen scarcity in the upper atmosphere, maintaining full power output across extended climbs. Japanese radial engines, such as the Mitsubishi Hama 33 or Nakajima Hard 45, suffered power loss of up to 35% at similar altitudes. Interrogation of captured aircrew from a forced landing incident on Kyushu provided additional insight. Crew statements described controlled gun turrets operated through the General Electric Central Fire Control System. Each turret linked electrically to a computing site correcting for airspeed, angle, and target range. This mechanism allowed defensive coordination far exceeding the manual gunnery systems of previous bombers. Testing of captured gun assemblies demonstrated remote actuation accuracy within a margin of 0.6 degrees. For Japanese analysts, this precision confirmed why conventional head-on attacks resulted in catastrophic losses. Flight data recovered from the B-29's instrument cluster indicated cabin pressure maintained at 8,000 foot equivalent even during 31,000 foot operations. This allowed crews to sustain endurance missions exceeding 14 hours without physiological degradation. Operational documents retrieved from damaged aircraft recorded fuel capacity of 7,000 gallons distributed among self-sealing tanks. Range and payload data demonstrated that the bomber could deliver 10,000 pounds of ordnance over a 3,000-mile radius. No Japanese twin-engine bomber possessed even half that capability. Wind tunnel tests at the University of Tokyo attempted to replicate B-29 aerodynamic contours using wooden models. Results confirmed laminar flow characteristics across the wing root and stabilizer surfaces, achieved through exact manufacturing tolerances impossible in wartime Japan. The Technical Evaluation Committee concluded that such aircraft could not be countered by incremental improvement. Instead, complete redesign of engines, superchargers, and airframes would be required, beyond Japan's industrial reach by 1945. Reports submitted to the Imperial General Headquarters estimated that even under emergency conditions, a domestic equivalent could not be produced in less than 3 years. Parallel research into high-altitude interception focused on the Keel 87 and J7W1 prototypes, both still incomplete. Engine failures during test climbs underscored the technological gap in metallurgy and turbocharger manufacture. Japanese intelligence further identified that each B-29 incorporated extensive fire detection and co-suppression systems, rare even in German aircraft. Operational endurance at extreme altitude proved not merely an engineering advantage but a cumulative outcome of industrial resources. Analysts summarized their findings in February 1945. The American bomber is an airborne factory. Its systems exceed our present scientific production methods. From these investigations, the Imperial staff understood that Japan was no longer confronting superior tactics, but superior engineering infrastructure. The conclusion was not ideological but mathematical. Their highest sky had become an unreachable domain controlled by American industry. By early 1945, repeated engagements confirmed the operational supremacy of the B-29 over the Japanese home islands. Air defense records from the 10th Air Division listed an interception rate of less than 5% per incoming formation. Even successful climbs rarely resulted in sustained firing contact before the bombers exited engagement altitude. On February 25, radar logs from the Kanto sector recorded 274 enemy aircraft over Tokyo at 31,000 feet. Japanese fighters launched from Chofu Airfield failed to close distance before fuel exhaustion forced withdrawal. Ground controllers noted that interception windows averaged less than 90 seconds per sortie. Loss reports indicated unsustainable attrition among Raiden and Hay-8 units attempting vertical pursuit. By March, operational doctrine shifted to concentrated flak zones, but range limitations persisted. Only the Type 88 100mm anti-aircraft gun could theoretically reach B-29 altitudes, yet accuracy fell below 1 hit per 2,000 rounds. Thermal distortion, wind drift, and radar inaccuracy further reduced effectiveness. Post-mission analysis by the Air Technical Intelligence Division confirmed that American bombers maintained formation integrity throughout Japanese defensive fire. Each aircraft's internal pressurization prevented crew incapacitation from near-miss explosions. Radio monitoring recorded tight coordination between bomber groups using encrypted VHF channels unknown to Japanese intercept operators. Observers noted identical airspeed and altitude data across dozens of aircraft, confirming mechanical precision and centralized mission control. By mid-March, Imperial headquarters circulated a classified memorandum acknowledging the impossibility of altitude-based defense. The memorandum concluded, "Enemy heavy bombers operate in the stratosphere. Our weapons are designed for the troposphere." This phrase became a quiet recognition among staff officers that Japan's technological reach had ended below the clouds. Further evaluation showed that American logistical throughput supported continuous operations without pause. Every 10 days, new formations arrived from the Marianas, replacing losses before Japan could adjust tactics. Field officers reported that even if one raid destroyed an airfield, replacements were flown in within 48 hours. Maintenance documents captured in Saipan revealed a standardized parts distribution system ensuring consistent mechanical readiness. Each B-29 fleet achieved operational availability above 80%, an unheard-of figure for multi-engine bombers. Japanese commanders compared this to the domestic average of 38% readiness for twin-engine types under war conditions. Engineers at Tachikawa and Yokosuka realized that the key variable was industrial continuity, not isolated design. American factories produced not only aircraft but the precision tools that built them, creating a production cycle self-sustaining in quality. This industrial recursion had no counterpart within Japan's fragmented wartime supply network. By April 1945, the Imperial Staff's Aeronautical Section formally ceased recommending high-altitude interception as a feasible defense measure. Instead, resources shifted toward night operations, balloon defenses, and research into suicide interceptors. Privately, senior officers conceded that such measures would not alter the outcome. Reports written in April used clinical phrasing but conveyed clear defeat in tone. "We cannot reach them." That was the final consensus. The B-29 was not merely higher, it existed in a separate layer of war, mechanical, numerical, and unreachable. From every vantage point below, Japanese observers continued to watch the vapor trails moving across the stratosphere, silent markers of a lost dimension. The emergence of the B-29 program illustrated the United States' capacity to merge scientific precision with mass production. By early 1945, over 1,400 operational superfortresses were assigned to the 20th Air Force. Each airframe represented more than 60,000 labor hours drawn from a national network of subcontractors and assembly plants. The Boeing, Bell, and Martin companies shared standardized blueprints allowing components to be interchanged without adjustment. Subassemblies were transported by rail and barge across the continental United States to meet assembly schedules defined to the minute. Supporting this infrastructure were metallurgical plants, optical workshops, and computing instrument factories producing the necessary guidance equipment. In parallel, the U.S. Army Corps of Engineers constructed advanced bases in the Pacific within weeks of capture. On Tinian Island, for parallel runways each measured over 8,500 feet in length, the largest airfield complex of the war. Fuel depots stored more than 100 million gallons of aviation gasoline, supplied through uninterrupted naval convoys. By comparison, Japan's total domestic monthly fuel refinement had fallen below 500,000 barrels by spring 1945. The logistical asymmetry was therefore a ratio exceeding 200-to-1 in sustained air operations. Production figures from the U.S. War Department show that between January and May 1945, American factories delivered 500 new B-29s and 1,200 spare engines. Japanese aircraft production during the same period decreased by 40% due to bombing damage and raw material shortages. Industrial reports from Nagoya and Osaka confirm repeated loss of aluminum stockpiles and forging equipment. The disparity in altitude warfare capability originated from these cumulative conditions rather than from tactical doctrine. American crews benefited from a fully mechanized support chain, including radar calibration, ground-based navigation, and real-time weather analysis. Japan relied on optical tracking and paper maps drawn from pre-war survey data. By the time Japanese interceptors launched, B-29s had already adjusted course based on high-altitude wind models transmitted via radio relay. The result was predictable: each raid achieved statistical accuracy beyond any previous air campaign. Strategic assessments compiled after the war by the U.S. Joint Chiefs of Staff recorded average bombing dispersion within 1,000 feet of target centers. For Japan cities, dense, flammable, and inadequately defended, the effect was cumulative devastation. Industrial areas in Tokyo, Nagoya, Kobe, and Osaka lost more than half their productive capacity by mid-year. The Imperial General Headquarters reported to the War Ministry that aircraft production was no longer measurable. These figures represented not only destruction but a demonstration of altitude supremacy's industrial consequences. The B-29 campaign compressed Japan's economic resistance into months rather than years. Each sortie represented an intersection of metallurgy, computing, and logistics, fields in which Japan could not compete. Intelligence analysts later described this transformation as the first instance of fully industrialized air warfare. Every component of the B-29's success, pressurization, turbo-supercharging, centralized fire control, and fuel logistics, was traceable to pre-war American industry. By 1945, it was no longer a contest of pilots but of production. The Japanese air staff recognized that no adjustment in training or bravery could offset that equation. In technical memoranda preserved at the National Institute for Defense Studies, one summary line recurs across multiple departments. The enemy controls altitude because he controls industry. It was a concise statement of the strategic imbalance defining the war's final phase. From the ground, Japanese observers continued to record the contrails crossing unchallenged over their homeland, symbols not of tactics, but of an industrial revolution waged from 30,000 feet. Following Japan's surrender in August 1945, technical missions from the United States and Allied powers inspected remaining air defense facilities. At Tachikawa, engineers found incomplete prototypes of the Kyo-87 and J-8M1 high-altitude interceptors, both halted by lack of turbo-supercharger components. Blueprints revealed ambitious designs capable of reaching 39,000 feet, but only on paper. Production bottlenecks, fuel scarcity, and metallurgical limitations had rendered such concepts theoretical. Interviews with surviving officers from the First Air Army described a gradual understanding of futility rather than sudden defeat. They noted that, by summer 1945, air alarms had become routine exercises without expectation of engagement. Observation units still tracked contrails, but command no longer issued scramble orders unless bombers descended below 25,000 feet. Post-war reports compiled by the U.S. Strategic Bombing Survey confirmed this operational paralysis. The survey concluded that the B-29 campaign demonstrated decisive application of industrial capacity to strategic range and altitude. Captured Japanese research papers were translated and archived by the Air Technical Intelligence Group at Wright Field. These documents recorded minute technical comparisons between Japanese and American systems, each ending with a quantified performance deficit. Turbocharger efficiency, cockpit temperature control, and airframe precision machining all measured significantly below American standards. In interviews conducted at war's end, Japanese aeronautical engineers acknowledged the limitations of their industrial base. They cited absence of high-octane fuel, shortage of precision lathes, and lack of automated casting equipment. Former officer reports used exact figures. In 1945, Japan possessed fewer than 200 machine tools capable of sub-millimeter tolerances. The United States had over 40,000. This ratio defined not only production but the mechanical reality of altitude warfare. Post-war evaluations by the Allied Occupation Scientific Intelligence Division confirmed that Japan had reached the upper limit of pre-war metallurgy. Even experimental alloys failed under sustained supercharged pressure at 30,000 feet. The B-29 thus represented more than a bomber. It embodied a system of applied science beyond national recovery at wartime scale. In lectures delivered in 1946 at the University of Tokyo, Professor Hideo Itokawa summarized the experience. The lesson of the Superfortress is not flight, but the engineering civilization that built it. American archival reports recorded similar conclusions from the U.S. Army Air Forces. The campaign proved that altitude, precision, and mass production could converge into a single strategic weapon. Later aircraft, such as the B-36 and B-47, continued this lineage, but the principle originated in the B-29's 1944 operations. For Japan, the era of piston engine interception ended with the contrails above Tokyo. The nation's air defense system, based on proximity and range parity, had been rendered obsolete by altitude asymmetry. By 1946, surviving Japanese airfields served as test sites for American evaluation units. Captured Ki-84s, Raiden, and Shiden fighters were flight tested against B-29 airframes to confirm the performance differential measured in combat. Results consistently showed a gap of 6,000 to 8,000 feet in sustainable climb altitude, exactly as wartime observers had recorded. Archival films showed Japanese officers watching these demonstrations silently, noting figures but offering no comment. Their notebooks contained precise entries, but the conclusion was already known: the sky once defended had passed irreversibly into enemy control. By the close of the occupation's first year, Japan's aviation industry had been dismantled, its laboratories repurposed for civilian study. The contrails no longer appeared overhead, but their legacy remained as a record of scientific disparity measured in altitude, horsepower, and precision. When post-war engineers reviewed the wartime data, they marked one final notation. The moment the B-29 appeared, the defense of Japan ended at 30,000 feet. In the years immediately following 1945, Allied and Japanese technical committees collaborated to compile complete evaluations of the B-29's influence on the Pacific Air War. These findings were later declassified in the U.S. Strategic Bombing Survey's final report, The Effects of Air Attack on the Japanese War Economy. Data revealed that high-altitude operations had reduced Japanese industrial output by more than 50% within 8 months. The report attributed this efficiency to uninterrupted logistical chains, standardized parts interchangeability, and precision bombing at previously unattainable altitudes. Japanese analysts who reviewed these documents post-war confirmed that interception failure was not primarily tactical, it was mechanical. The altitude gap between the B-29 and available interceptors was recorded as 7,200 feet on average. Even with emergency power, climb performance of the J-2M Raiden decreased sharply above 28,000 feet due to loss of supercharger pressure. In parallel, Japanese radar systems such as the Type A-1 and Takai-6 showed limited range and poor high-altitude discrimination. Their performance degraded significantly above 25,000 feet because of signal attenuation in the stratosphere. Consequently, the B-29 formations were often tracked only after bomb release, making interception reaction times negligible. American post-war analysis confirmed that defensive loss rates for B-29 units averaged below 1% per mission over Japan. This statistic demonstrated operational dominance through altitude rather than numbers alone. Surviving Japanese pilots interviewed by occupation authorities repeatedly cited the same phrase: they were above the sky we could reach. Their testimonies were factual, not rhetorical, derived from measurable flight performance records preserved during the war. In 1947, the Allied Technical Air Intelligence Unit examined remaining Japanese airframe projects intended for high-altitude interception. Among them, the turbocharged Ki-94-2 design could theoretically reach 40,000 feet, but its prototype never left the drawing phase. The jet-powered J-8M1 Schussway, adapted from the German Me-163, completed only one flight before engine failure destroyed the aircraft. These post-war inspections confirmed that Japan had understood the problem scientifically but lacked the industrial ecosystem to execute a solution. Engineers concluded that the war's decisive variable was not innovation but reproducibility. The B-29 program proved that complex systems could be mass-produced without sacrificing performance. This principle formed the foundation of post-war American aerospace development and influenced design philosophy worldwide. In Japan, demobilized scientists who later contributed to civilian aviation cited the Superfortress as the model of integrated engineering discipline. Archival documents from 1948 show Japanese universities using B-29 components as teaching material for metallurgy and aerodynamics. These fragments, wing spars, propeller hubs, and turbocharger housings became instruments of education rather than warfare. By then, Japan's air research had transitioned fully to non-military purposes under Allied supervision. Yet within technical circles, the lessons of altitude warfare remained explicit and unembellished. Altitude superiority had not been achieved through secret weapons or pilot skill, it had been manufactured in factories, measured by tolerances, and maintained through logistics. For the observers who once watched the Superfortresses cross 30,000 feet, the conclusion was exact and permanent. The sky, once a field of combat, had become a measure of industrial civilization.